Welcome to the first lecture video in our second class time series of lecture videos. I know after the interesting revelations about resonance forms and molecular orbital theory, now we have to get down into, the messy reactions of these interesting, allylic systems. And yeah, it can be kind of trying. So we'll try to make this as painless as possible and talk about some interesting subjects that can get wrapped into discussions of these types of reactions. So to start with our discussion of reactions at the allylic position, we're going to consider radical allylic halogenation. So here we have our most simple system, our propene. And if we react that with some halogen, so X is a typical symbol that we use for generic halogen, and they generally come in diatomic forms. At low concentration, using either heat or light, we end up generating an allylic radical that goes through a radical chain reaction, and we, usually end up halogenating that allylic carbon. And of course, the byproduct is HX. So something to note, a high concentration of our halogen would favor the addition. We talked about this in the first semester, addition of halogens to pi bonds. But if we've got our halogen at low concentration with the heat and light, we're going to do a radical mechanism. So let's consider a radical mechanism for propene and diatomic chlorine reacting at 400 degrees C to give us 3-chloropropane, or allyl chloride as we know it, and HCl. But before we consider that radical mechanism, before we launch into that, we should probably let you know that all radical reactions have 3 steps. And so what are the 3 steps? Well, we've got initiation that starts the reaction, propagation, where we transform one radical into another radical, which continues the reaction, and then termination, which of course ends the reaction. So we end up with no radicals at the end of a termination step. So in initiation, radicals are generated. We need heat or light to break bonds homolytically. So here we've got our diatomic chlorine. That's the weakest bond. We're breaking it with heat. We form 2 chlorine radicals. The dissociation energy for that is 58 kcals per mole. And then of course our chlorine radical bumps into our propene, and in fact the allylic carbon hydrogen. And what happens is we abstract that hydrogen and we form the allylic radical. Now, there's a certain energy associated with breaking this bond homolytically, and there's a certain energy associated with forming the HCl bond, right? And we'd be able to calculate that if we knew what those energies were, the entire, change in enthalpy for this step. In the second step, our allyl radical then bumps into diatomic chlorine. It would be less statistically likely for our allyl radical to find a chlorine radical in this mixture because, we only generate a small number of radicals at any given time. But in this second propagation step, we reform a chlorine radical, which goes back to step 1 and finds its own propene to react with. And of course, it creates our product, one of our products, our allyl chloride, right? Another product, the HCl, is produced in that first propagation step. So there we have step 2. The allyl radical abstracts a chlorine atom from diatomic chlorine and regenerates our chlorine radical. To finish this up, this particular lecture video, we've got to talk about termination. So radicals are destroyed. Yes, while it's statistically unlikely, you might have a couple of allyl radicals bump into each other, forming this 1,5 hexadiene, or your chlorine radicals might recombine to form diatomic chlorine. Radical bromination. I suppose we can broach this topic before we move on to discuss more radical reactions. Common conditions are N-bromosuccinimide, NBS, in carbon tetrachloride, so CCl4. So what is NBS? This is N-bromosuccinimide. It's an interesting molecule which will react with trace hydrobromic acid, HBr, to form succinimide and a low concentration of diatomic bromine. Diatomic bromine, of course, has a low dissociation energy, so we can do radical reactions with it. What's nice is NBS is insoluble in carbon tetrachloride, so we can simply filter it off at the end of the reaction. And the suspension provides a steady source of a low concentration of diatomic bromine. And so one could think about forming allyl bromide by reacting propene with NBS in carbon tetrachloride with a little light. And it's an identical mechanism to the radical chlorination. And of course, diatomic bromine is generated in low concentration first. So I think that's where we'll wrap this particular first video up. We'll talk about the bromination of 1-butene next in our second lecture video, and I will see you soon for that.